Okay. So as we have started discussing about cubic unit cell in last lecture, there we just know that cubic means A equals to B equals to C, and then alpha, beta, gamma, all of them are equal to 90 degree. Yes. So here we are going to study in details about cubic unit cell. What are the details we are going to study here? First thing is the effective number of lattice points. Effective number of lattice points where? Effective number of lattice point in primitive, base-centered cubic and body-centered cubic. Because in primitive means we have lattice points or atoms only in the corners. Face means corner plus face. Body means corners plus inside the body. So obviously the effective number of lattice point will be different for all these cases. Then we will find also their coordination number. That is number 2. Now what is coordination number? Coordination number means number of nearest neighbor. Take any lattice point and how many number of nearest neighbor are there. That means it will be in touch with other lattice point, how many neighbors it is touching. So that's coordination number basically. Then we'll find the relation between atomic radius and lattice parameters. So atomic radius, atoms definitely will have some radius, and we'll find the relation with lattice parameters. Who are lattice parameters? These are A, B, C or alpha, beta, gamma. Mostly we'll find in terms of the sides. So one more thing, A, B, C, since all of them are equal, we can write all of them as equals to A. Okay. And lastly, we will find packing fraction. That should be an important concept. Packing fraction means, see, an unit cell means it's a cubical unit cell. We are taking all sides are equal, all angles are 90 degree, well enough. Now if we have lattice point on the corners, the atoms are spherical in nature. This cube is not spherical. So when we take this cubic spherical lattice points together, there will be some gap between them. So whatever is the volume of the unit cell, everything will not be occupied by the lattice points or atoms. Some gap will be there. Packing fraction tells us out of the total volume of the unit cell, how much is occupied. So then by the, obviously we can find how much is vacant also. So let us move there, finding one by one. So for simple cubic, you can see the diagram here. There are 8 corners in this cube. We are saying the lattice parameter is A because all sides are equal. All can be said as A. A, B, C equals to A only. Now you see there's this. How many corners were there? Number of corners. Number of corner is 8. But this from every corner, if we take like this one unit cell, this corner atoms, all the corner atoms are touching each other. You can see here, this corner atom is touching each other, right? This another corner atom, another corner, all these corners are touching each other. But with how many nearby unit cell this corner is sharing? We have to know this very carefully. So we'll see, suppose this one, if we grow this unit cell on the right hand side, we are getting another unit cell. If we grow this unit cell on the top, we are getting another unit cell. If we grow this unit cell on the front, we are getting another unit cell. So in this floor only, suppose this is the terrace of some building. If you think like this, consider this as your origin. Okay, we can take anyone as origin because all of them are identical. Any point as we can take origin. For time being, we are taking this point as origin. So this is one unit cell. In this ground floor, there will be 1, 2, 3, 4. So in the ground floor only, this corner is shared with 4 unit cell. So if we start building this unit cell on the top floor, then 4 more, above 1, 1, and 1 more, above 2, 1 more, above 3, 1 more, above 4, 1 more. So how many unit cell this lattice point is being shared with? 8. So this total is divided into 8 part. This unit cell, if we take this one, it is only taking 1/8 part of this corner atom. Similarly, if we take other corner atom also, how many corner altogether? Total 8 corner. So from every corner, we have contribution of only 1 by 8 because every corner is shared with nearby 8 unit cell. How? Just now we have seen that in this floor only 4. Top floor 4 more, 4 plus 4, 8. So what is the effective number of lattice point then? Effective number of lattice point is 8 into 1 by 8. 8 why? There are 8 corners. 1 by 8 why? Because from every corner we have 1 by 8 contribution. So this is equals to 1. So is this a primitive or non-primitive unit cell? Simple cubic is a primitive unit cell. Sometimes in exam, they do not ask to find details of simple cubic. They will say just primitive cubic cell. Then you have to definitely understand that when they are talking about simple cubic, that is lattice points are only in the corners. Done, number 1. Number 2 is coordination number. Yes, coordination number means nearest neighbor, right? So nearest neighbor, you can see if we take this corner atom only, how many corner atom it is touching altogether? Left, right, top, bottom, front, back. So it is touching, it is shared with unit cell 8. This student has confusion that ma'am it is sharing with 8 unit cell. That's why you took 1 by 8. And now you are saying coordination number is 6. How? So see this if this lattice point is here, 1 like this we go, right? 1 is left and right. 1 is top and bottom. One other is front and back. So how many are there altogether? There will be 6 coordination numbers. So this lattice point is touching only 6 nearby lattice points. So coordination number is 6. Next, coming to the third point, relation between atomic radius and A. You see here this is A, right? From one corner to other corner. How many radius are there? 2 radius are there. This is one radius. This is another radius. So R plus R equals to A. That is 2R equals to A, or R equals to A by 2. Yes. So R equals to A by 2. Here it is written in capital R. Capital R equals to 0.5. 0.5 means half only. So half of A. So now we are going to find the atomic packing fraction. So the relation we know is, okay, so one by one we'll go atomic packing fraction we have found. Now our job is to find the relation, right? Relation we also know that R equals to A by 2. R is atomic radius, A is lattice parameter. Now last is atomic packing fraction. APF is nothing but atomic packing fraction. Here we see atomic packing fraction, how we are going to find. What is the total volume of the unit cell? Unit cell is cubic. We know for any rectangular cuboid, the volume is length, breadth, height. If length, breadth, height all equals to A, then the unit volume will be A cube. Now atoms, we are considering them to be spherical. What is the formula for sphere volume? 4 by 3 pi r cube. So 4 by 3 pi r cube. Instead of r, what we are taking? 0.5 A or half of A. And why we are multiplying with atoms of unit cell? 1, why we are multiplying? See, total volume of unit cell is A cube. Total volume of one lattice point is 4 by 3 pi r cube. Yes. But is there only one lattice point? There can be more than one lattice point also. In simple cubic, we have only one lattice point. That's why we are multiplying 1 with 4 by 3 pi r cube. This is nothing but r cube. Okay. So if we do this, we are going to get 0.52. In percentage, if we want to find percentage, then 0.52 into 100 percentage, that is 52%. That means in an unit cell, whatever is its volume depends on A. If A is big, volume is big. So out of the total volume, only 52% is occupied by lattice point. Remaining part is vacant. So that is true for simple cubic. Okay, so it has to be very clear that why atomic packing fraction is 1 into 4 by 3 pi r cube by a cube. 1 comes because we have one lattice point. 4 by 3 pi r cube, why? Because this is spherical. A cube, why? Because this is cubic, all sides are equal. Next, moving to face centered cubic. In here we can see very clearly, we shall go one by one, right? First we should find effective number of lattice point. So how many corners are there? 8 corners, and we all know every corner is shared with 8 unit cells, just similar to simple cubic. Okay, so 1 by 8, 8 into 1 by 8. 1 by 8 is the contribution from every corner. There are 8 corners. Now how many number of faces are there? Top, bottom, front, back, left, right, like that we will have 6 faces. So there are total 6 faces. Now with how many unit cell this face points are sharing? If we have a left one right now, suppose this is here, I'm drawing a diagram. So this left, right, top, bottom, we are going to say, right? So this is left, this is right, this is left for this unit cell. If we draw another unit cell on the side, this is right for another unit cell. So it is shared with this and this. Top one is shared with this and this. So every face is shared with 2 unit cells. So 6 into 1 by 2. Okay, so 1 plus 3, 4. So what is the effective number of lattice point in face centered cubic? 4. Is it a primitive unit cell? No. Primitive unit cell means effective number of lattice point should be 1, but here we have 4. So that is done. Now let us move to coordination number. Okay, so coordination number is tricky for this case, face centered cubic. See this diagram very carefully. So we know we are living in a 3-dimensional world, and these crystals are also 3-dimensional only. It has 3 dimension, means x, y and z. You can name anything. So here I have shown 3 planes. This is plane number 1, plane number 2, plane number 3. Plane 1 is kind of floor. Okay, so floor or terrace where we're standing. Then plane number 2 is another wall. Plane number 3 is another wall. Okay, so this is one plane. This plane is 1. This is 2. This is 3. Now in every plane, this face atom is sharing with face lattice point is sharing with how many corners? You will see. So this is a corner atom. It is sharing with face on the floor 1. It is sharing with 2. It is sharing with 3. It is sharing with 4. So in plane 1 only, this corner atom is touching 4 face atom. Yes, you can see in this diagram again, left side diagram. This corner atom is touching this corner atom is touching this face. Yes. Then similarly it is touching on this floor only. If we go up like this, 2, another like this, 3, another like this, 4. So that diagram only here. Okay, so this is touching 4 face atom on the floor. Similarly, this is plane 1. Again in plane 2, it will be touching another 4 faces. Again on plane 3, it will be touching another 4 faces. So there are 3 planes altogether. For every plane, 4 each corner atom is touching 4 face atom. So 3 into 4, 12. So the coordination number of face centered cubic is 12. So if that is being done, we shall move to finding the relation between A and R. Now let us move to our next slide. So this is face centered cubic. How many faces are there? 6 faces. How many corners are there? 8 corners. Corner atoms are shared with 8 unit cell. Face atoms are shared with only 2 unit cell. Effective number of lattice point is thus 4. Coordination number is 12. This is coordination number. That is effective number of lattice point. Okay. So now faces, 6 faces. I will write this as front face 1, back face 2, left face 3, right face 4, top face 5, bottom face 6. So now you see corner atoms are not touching one another like it used to touch in case of simple cubic. Yes, corner atoms are touching one another. But when we go to the face-centered cubic, there is gap between this corner atom. They are no more touching each other. Why? Because face-centered is there. So it is like pushing apart the corners. So we can, when we find nearest neighbor, we cannot say that two corner atoms are nearest neighbor. Who is nearest neighbor here? From one corner to other face is now nearest neighbor. So that's how we found coordination number also, right? So now from this one corner to other corner, from this one corner to other corner, this distance is a. From everywhere, this edges are a. What is the value of face diagonal? Face diagonal means what? From one corner to other corner will go via the face, cutting through the face. That is face diagonal. If you go from this corner to this corner, this is another face diagonal. This face diagonal must be equal because we are talking about cubic system. So you will use the Pythagoras theorem. This is also a, this is also a. Using Pythagoras theorem, how much is this? A square plus a square plus a square root. So it will be root of 2a. So this face diagonal is root 2a. Will it be different for different face diagonal? If we take from here to here, this is also face diagonal. We go from this point to this point, cutting the face. This is also root 2a because this side a, this side is also a. That is well enough. We know the from one face to other, one corner to other corner via the face, it is root 2a. But how many radius are there? Here radius r, here radius r plus r, 2r, another r. So it is taking half of lattice point, corner again half of lattice point, inside full. Full means 2r. R if the radius, okay? Sometimes we write capital R also, no problem. Have to be consistent whatever we are choosing, okay? So we are getting 4r equals to root 2a. So from here r equals to root 2a by 4. This formula is important to find atomic packing fraction, okay? So atomic packing fraction, here now we are going to find atomic packing fraction. Relation we found, yes, a equals to just now what we found, r equals to root 2a by 4. R equals to root 2a by 4. How we found? See here r, here also r. This whole thing is 2r if the radius is r, okay? So diameter is twice of r, right? So we found that r, capital R or small r, you can take anything. You have to be consistent anyhow. So let us move to this relation also found. Let us move to atomic packing fraction. What do we know atomic packing fraction? Out of the total volume of unit cell, how much is occupied by lattice point? How many lattice point are there? Effective number of lattice point is 4. We found this one. So we have to multiply 4 with the volume of each lattice point. Each lattice point volume is how much? 4 by 3 pi r cube, like any sphere. So instead of r, we are writing root 2a by 4. So that this a cube will cancel. Ultimately, we are going to get atomic packing fraction as 0.74. So this, we should not forget about 4 here. In simple cubic, it was 1 because only effective number of lattice point was only 1. In face-centered cubic, effective number of lattice point is 4. So we are multiplying 4 with 4 by 3 pi r cube. What is the volume of one sphere? What is the volume of 4 sphere? Volume of one sphere multiplied by 4 divided by a cube. So this, instead of r, we are writing root 2a by 4. So now let us move, we are done with this one. So 0.74, if we take percentage, it will be 74%. How we are going to do that? 0.74 into 100%, 74%. So how much is filled? 74% is filled. And remaining 26% is vacant. So compared to simple cubic, face-centered cubic is tightly packed. In cubic, how much was, I also forgot, it is 52% is occupied, whereas in face-centered cubic 74% is occupied. Now let us check body centered cubic. Before going to body centered cubic, you can guess whether packing fraction will increase or decrease. Any idea? So let us go and do the calculation. Yes, so this is body centered cubic. We have lattice point in the corners. How many corners are there? 8 corners. Each corner is shared with 8 remained adjacent unit cell, 8 into 1 by 8, plus inside the body. So now whoever is inside the body, is it shared with any other unit cell? No. So it is completely, the whole lattice point is inside this unit cell. So 8 into 1 by 8 plus 1, that is 2. This is effective number of lattice point. Effective number of lattice point for body centered cubic. So body centered cubic is primitive or non-primitive? This is also non-primitive. Effective number of lattice point is 2. Then next we will move to finding the coordination number. So coordination number, again what? Coordination number same. It's a number of nearest neighbor. Here also you can see corner atoms are not touching each other. There is gap between them because the body centered is pushing them, right? Now all the corner atoms are touching body center. That is true. That is visible from this diagram. So how many corners? 8 corners. So every body centered is touching how many corners? 8. So coordination number is very simple in this case, 8. Because every body centered atom or lattice point is touching how many corners? Is touching 8 corners. So coordination number is 8. Next is relation between A and R. A is what? Lattice parameter. R is what? Radius. Now you can see, so if we see from the corner, they are not touching. From this corner to this corner, there is gap, you can see. If we go via the face, from face diagonal, cutting through the face, then also atoms are not touching. But if we go via the body diagonal means we have to pass from one corner to the other corner via the body, from inside the unit cell. Then it is touching how many lattice point? You see half of this one. So half of this lattice point means radius is R. Half of again this one. So this is also R. This is touching completely. Completely means 2 of R. Till this half is R radius, another half is radius R. R plus R, 2R. So body diagonal, we can say body diagonal. What is the meaning of body diagonal? Passing through the body, inside the body. Body diagonal equals to 4R. It is touching altogether 4 radius, or 3 lattice point, but this is 4R. Okay. Now, do we know the value of body diagonal in terms of A? Yes, we can find that. We know all the sides are A. This is also A. This is also A. We know the value of face diagonal. Yes or no? This face diagonal from how much we found? In face centered cubic, face diagonal we found it to be root 2A. So again we'll use Pythagoras theorem. So we know face diagonal is root 2A. This side is A. So using Pythagoras theorem, this is hypotenuse. So what will be the body diagonal will be equals to root 2A square plus A square. This side is root 2A. This side is A. A square plus root 2A square will give you the body diagonal. So from here what we are getting? 4R equals to root 2A square means root 2 square. Root cancels, so 2A square plus this is A square. So this is 3A square. R equals to sorry, this is 4R square, this square, right? Body diagonal square. So 4R square equals to 3A square by 4R. Just I'll clear this thing. Yes. So body diagonal is how much? We know that this is 4R and this is equals to square root of root 2A square plus A square, that is root of 3A square. This is 4R square. So if you take this, take out the square root, sorry, you have to don't take the square root. So R equals to root 3 by 4A. because this is square root cancel, so root 3 4 by A. This is the relation between R and A. Now let us find the atomic packing fraction. What is the volume of unit cell? Just same to previous cases, A cube. What is the volume of the lattice point? 4 by 3 pi R cube. Yes, R is equals to how much? Root 3 4 by A. So that's one, we are, instead of R we are writing root 3A by 4. Why we are multiplying 2? Because effective number of lattice point is 2. One lattice point volume is this 4 by 3 pi R cube. What is the volume of 2 lattice point? 2 into that. So 2 into this, if we do, divide by A cube. This is also A, it will give you A cube. This also A cube will get cancelled. And you are going to get the packing fraction as 0.68. In terms of percentage, it is 68%, 0.68 into 100%. So how much is occupied in body-centered cubic? 68%. So if we take a relation, who has the highest packing fraction? Face-centered cubic is highly packed. Then we have body-centered cubic. Then we have simple cubic. Face-centered cubic, how much it was? Let us just revise once. It was 74%. Face-centered cubic, 74% was occupied. Body-centered cubic, how much occupied? 68% occupied. Simple cubic, how much? It was 52%. So sometimes question is also asked, like find the atomic packing fraction of a cubic system which has the highest packing fraction. Then you need to discuss, okay, highest means obviously they are asking about face-centered cubic. Sometimes they will say find the packing fraction of primitive cubic unit cell. Primitive means which one? Simple cubic, because simple cubic has effective number of lattice point 1. Body-centered cubic has 2, and then face-centered cubic has 4. So body-centered, face-centered are not primitive. Only simple cubic is primitive. So this is the table of comparison for the 3 cubic system we have discussed: simple cubic, body-centered cubic and face-centered cubic. In all the cases, unit cell volume is A cube. Effective number of lattice point 1, 2, 4. Then coordination number simple cubic only 6, up, down, left, right, front, back. Body-centered cubic 8. How it is 8? Because every body-centered atom is touching nearby 8 corners. Okay, face-centered cubic 12. It was a little bit tricky. You have to see the diagram. If you want to go back and see that there are 3 dimensions altogether. Every dimension that corner atom is touching 4. So 4 into 3, 12. 3 dimension, every dimension 4 faces. So 3 into 4, 12. Nearest neighbor distance. In simple cubic, corner atoms are touching, so this just A, and then this one is A. This is all our R equals R value. Okay, then atomic radius, this is A by 2, this is A root 3A by 4, this is A by 2 root 2. Packing fraction 0.58. In terms of fraction, if we write in percentage, we just have to multiply by 100 and write percentage. Then it will be 52%, 68% and 74%. Which is the highest pack, highly packed? FCC. Lowest pack? Simple cubic. Okay. So in next lecture, we are going to discuss about Miller indices and interplanar spacing.